Hello everyone, and thank you all for joining me here today. My name is Dejan. I'm very happy to be here, and today I'll talk about Kotlin Simple Processing, or KSP for short. In today's talk, I'll try to explain what KSP is, how it works, and when you should consider using it. So I hope you'll enjoy this talk and learn something new. Before we get into the topic, I'd like to start by giving you a bit of background about myself. I'm doing Android development for 7 years now, and to put that into perspective, when I started doing Android development professionally, Samsung Galaxy S8 and Pixel 2 were flagship phones. Currently, I work for a company called Endava, and previously I was part of a company called 5, which was officially Google Developer Certified Agency in 2018, which was later acquired by Endava. During this time, I've been lucky to work on large projects that have reached millions of users, with over 20 million downloads and more than 5 million users using our apps every day. Outside my day job, I also worked on a couple of book projects and numerous of tutorials as part of the Kotlin.com tutorial team, and I also given talks at large international conferences such as droidcon or such as AppDevCon. Also, I'll be giving away some promo codes for free digital books on Kotlin.com, so please make sure to stay until the end of the talk for a chance to win. Today I'll talk about Kotlin Simple Processing, so let's get into the topic. What is Kotlin Simple Processing, or KSP? KSP is a new way to do metaprogramming in Kotlin. But what is metaprogramming? In simple terms, metaprogramming means doing something else with the code you wrote. So metaprogramming is a technique that allows programs to inspect, modify, and act on their own code. Key features of metaprogramming include inspection, transformation, and code generation, meaning that the code can analyze itself, modify itself or other code, or even produce new code. Metaprogramming adds flexibility to code by allowing it to adapt to changes without manual intervention, and it also adds efficiency to code by reducing repetitive boilerplate code and enabling automation of tasks. Kotlin already supports several forms of metaprogramming. The first one is reflection. So, for example, you can use reflection in Kotlin to inspect class properties during runtime. Second form of metaprogramming is annotation processing. So Kotlin uses annotations to add some metadata to code, and these annotations can later be processed to influence code generation or compiler behavior. And also, Kotlin allows you to create your own custom annotations. And third way of doing metaprogramming are compiler plugins. So compiler plugins are powerful tools that extend compiler's capabilities and allow for code transformation during the compilation stage. Compiler plugins basically enable more advanced code manipulation and code generation techniques. So annotation processing is the most popular form of metaprogramming. Why can't we then just use Kotlin's annotation processing tool? Kotlin's annotation processing system is a system that's inherited from Java ecosystem, and this allows developers to easily migrate their tools from Java to Kotlin. However, this integration comes with a cost. Since annotation processing operates on Java language constructs, Kotlin-specific features such as properties or top-level functions are not directly supported. And to work around this, Build toolchain performs some tricks in order to enable this integration. However, this leads to performance issues during build times, and it can also sometimes generate confusing error messages. Another significant limitation of KAPT is that it is closely tied to Java ecosystem. So this means that annotation processors do not work with other targets that Kotlin can compile to, such as JavaScript or native. So this restricts the usage of annotation processing only to the environments where Java is the target runtime. What about compiler plugins? Compiler plugins are extremely powerful. Compiler plugins allow you to make an extensive changes to the behavior of the language and to the generated code. However, using compiler plugins also comes with some downsides. The APIs provided by Kotlin compiler are not guaranteed to be stable. So this means that these APIs can change with each new version of the compiler. Also, using these APIs requires in-depth understanding of compiler technologies and specific implementation of Kotlin compiler. And lastly, there's very little documentation on compiler plugins. So there's no an official guide on how to create a Kotlin compiler plugin. you basically have to go through Kotlin code and understand it yourself, which is not that straightforward. And this is where KSP comes into play. So KSP is a new meta-programming tool developed by Google that understands Kotlin-specific features. KSP is not tied to the JVM, so this means that it can be adapted to work on other platforms such as Kotlin Native or Kotlin JavaScript. KSP is significantly faster than KAPT, which is particularly important for large projects where build times are critical. So KSP reduces build time overhead that's imposed by KAPT. And lastly, KSP provides powerful yet easy to use API. We're going to see that on an example later on. When you look at the promotional materials from Google, they claim that KSP is up to 2 times faster compared to KAPT. Specifically, they're claiming that they're seeing performance improvements of processors like Room of up to 2 times when migrated to KSP. I haven't done any benchmarks myself, so I can't verify how accurate this is. Most of the popular libraries on Android already support KSP, and more are under development. So you can check out, in the screenshot and the link, you can check out the full list of libraries that support KSP, since this list is constantly being updated. Now, what are some use cases for KSP? Code generation is primary use case where symbol processors are used to generate new source code files, which reduces manual coding effort. So for example, Room persistence library on Android does exactly this. So it uses code generation to generate an abstraction layer over an SQLite. Second use case is code validation. So processors can enforce some rules and constraints during compile time, such as checking for API misuse or ensuring that the required annotations are present. So this helps prevent runtime errors, and it also helps catching issues early on in the development cycle. And beyond code, KSP can be used to generate other types of resources, such as JSON or XML configuration files based on some annotations in your code. In general, KSP can be used to save time and reduce errors by automating repetitive tasks. Let's now take a look into the basics of how KSP works. So when you first start working with KSP, first thing you have to do is you have to apply KSP Gradle plugin in your Gradle files. Since KSP Gradle plugin is hosted on Maven Central, you have to tell Gradle to search in Maven Central when applying the plugin. After that, you need to specify KSP version that you're going to use in your version catalog file if you're using version catalog. Important thing to note here is that each KSP version is strictly tied to the exact Kotlin compiler version, and for this reason, KSP version string has a Kotlin version in it. After specifying the version, you can apply the KSP plugin in the module where you're going to use KSP. So you have to apply the plugin, and you have to specify symbol processors that you're going to use inside of that module. To specify symbol processors, you're basically doing that as you would add any other third-party dependency, except that instead of using implementation or API functions, you have to use KSP function. In our case, we're specifying 2 symbol processors. The first one is third-party processor from the Room persistence library, since we are going to use this library in our project. And the second one is our custom symbol processor that's defined in a separate module inside of our project that we are going to implement later on. Let's now take a look into how KSP models Kotlin code. One of the design goals of KSP was to support Kotlin naturally. And as such, KSP's interfaces are modeled after Kotlin grammar. This means that if you are familiar with Kotlin code, you should be able to use KSP API with relative ease. And let's take a look into a conceptual example on how KSP models a Kotlin class with functions in a file. So when you have a Kotlin class like this inside of a file, KSP will give you access to symbols representing these elements. So when KSP starts processing this file, it will view my example class as a class declaration. In KSP, KS class declaration interface models class-like declarations. So this includes classes, interfaces, and objects. And for each class declaration, you can query for further details, such as member declarations or simple name, for example. KS function declaration interface models function declarations. In our case, we have two KS function declaration nodes, which represent myfunction1 and myfunction2 functions. Again, for each KS function declaration, you can query for further details, such as visibility modifiers, for example. We can also see here that KSP models Kotlin code by building a tree of nodes, and each of these nodes represents an element according to the Kotlin language grammar. So the example we looked at was a simplified example on how KSP models Kotlin class with its functions in a file. The full class diagram that KSP works with is a more complex. So the KSP's class diagram doesn't only include class and function declarations, but also properties, type parameters, annotations, and more. So in the screenshot and the link provided, you can check out the full extent of the class diagram that KSP operates with. In KSP, references to types are designed to be resolved explicitly by processors, because type resolution is one of the most expensive operations in the Kotlin compiler. And for this reason, there's this KS type reference concept that basically acts as a pointer to a type within Kotlin's type system. So whenever you reference a type in KSP, it's always going to be of KS type reference. And much of the information is actually available without resolution. So for example, type arguments can be obtained from KS reference element. If the original declaration referenced by KS type reference is needed, it can be obtained by resolving to KS type and accessed through kstype.declaration. However, processor should only resolve to a type when a specific information from KS type or KS declaration is needed. Now, KSP also comes with some limitations. So for simplicity and efficiency, no code modifications are allowed. So KSP is only supposed to generate new source code files, which are then compiled together with the original source code. Also, no expression level information is available to processors. This means that KSP can't get you further than a declaration. All that KSP can see or examine are the structures of classes and the signatures of functions. Let's now get into the practical part of this talk. So what are we going to build today? For the purposes of this talk, I built a very simple application that demonstrates capabilities of KSP. So in this slide, you can see the QR code and the link that will take you straight to the repository of this project. So all of the code samples and code snippets that I'm going to show in this presentation are simplified code snippets taken from this repository. So I encourage you to explore this project into more detail later on to see how a bit more advanced cases and some extra edge cases are handled. The application I built is a very simple application called People Hub. So it has a single feature. All that this app does is that it stores a list of people into a local database on a device. So it has a screen that allows you that shows a list of people from a database. It has a screen that allows you to add a new person into a database, and it has a screen that shows additional info about a specific person. What we are more interested about here is the architecture of our application. So in many common architectural approaches, such as clean architecture, for example, we create software models of entities based on our business or problem domain. And depending on the size of our project, we often define multiple layers inside of our project, where each layer works with its own data model. So a common variation that you can find in your projects are API models, data model, database models, domain models, and so on. And each of these models describe the same initial entity. In our case, since our application stores a list of people into a local database, we are going to work with database models, which represent database entities, and we are going to have domain models that the rest of the app works with. So for simplicity, we are only going to work with two types of models, database and domain. And this is how these models look like in code. So first we have a person data class, which is a domain representation of a person, and then we have person entity data class, which is database representation of a person. In general, when you have multiple representations of the same entity, these representations often only differ in a couple of properties, if they differ at all. In our case, for simplicity, these two representations are exactly the same. And since we have two types of models, we also need a way to map between them. And for that, we need these two mapper functions. So the first one maps from the database model to the domain model, and the second one maps from the domain model to database model. But we don't want to have these functions as the top-level functions, but instead we want to hide the map logic behind an interface. So for that, we need some kind of mapper interface and mapper implementation class components. Mapper interface defines mapping methods, and mapper implementation class implements mapper interface, and it contains the actual mapping logic. So this is the full component that we need in order to be able to map between our database and domain models. Now, we could write this component manually by ourselves, since it's pretty straightforward and it probably doesn't take a lot of time. However, each time we make some changes to our models, for example, we add new properties to it, we would also have to update our mapper component as well. So it would be nice if we could somehow automate this mapper creation process. And that's exactly what we are going to do today. So we are going to use Kotlin symbol processing to generate this exact mapper component based on annotations in our code. So let's get into it. First thing we have to do is we have to set up KSP within our project. Our project consists of three main modules: app module, annotation module, and processor module. App module is the main module that contains business logic and UI of our application. So it's the core module that the end user interacts with. Annotation module is a module where our custom annotations are going to be defined. So these annotations will be used by the app module to indicate that some component needs some kind of code generation or code processing. And finally, we have a processor module that will contain KSP code. So processor module will contain logic that will act upon our custom annotations defined in the annotation module. Processor module depends on annotation module because it needs to recognize the annotations from the annotation module, and app module depends on both annotation and processor module because it will use the annotations from the annotation module and it will use processors defined in the processor module. So to start, we are going to define our custom generate mapper annotation. So this is the annotation that we are going to use to annotate model classes that need their mappers automatically created. So we named this annotation generate mapper annotation, and it takes in one parameter named name. So the value of this name parameter is going to be used as the name for our interface component. We're also using retention meta annotation here and specifying source as the annotation retention. So this indicates that this annotation is only needed at the source level and not at runtime or in the binary outputs. And we're also using target meta annotation here and specifying class as the annotation target. So this means that this annotation can only be applied to class declarations. After we've defined our custom annotation, next component we have to define is a symbol processor provider. Symbol processor provider is a component that allows you to create an instance of your own custom symbol processor. To create symbol processor provider, we have to create a new class that implements symbol processor provider interface, which is part of KSP API. When we implement this interface, we have to override the create function. So create function will be called by Kotlin symbol processing to create an instance of a symbol processor. In our case, we are creating an instance of mapper generator processor, which is our custom symbol processor that we are going to implement in the upcoming slides. When it comes to the symbol processor provider, there are a couple of rules that we need to follow. Each symbol processor provider needs to be specified in a special file named com Google DevTools KSP processing symbol processor provider under the source main resources meta services part. And the content of this file needs to be the fully qualified name of your symbol processor. So all of these three conditions need to be met in order for symbol processor provider to work as expected. After we've defined symbol processor provider, we can finally define our symbol processor. So symbol processor is the main component that will contain the logic for code generation during compilation. To create a symbol processor, we again have to create a new class that implements symbol processor interface, which is again part of KSP API. In our case, symbol processor takes in two parameters, code generator and logger, which are used for creating new files and logging respectively. When we implement symbol processor interface, we have to override the process function. So the process function will be called by KSP infrastructure during compilation. Process function takes in one resolver parameter that gives us access to program structures such as symbols representing classes. Inside of our process function, all we do currently is we log a simple informational statement so that we can later verify if our symbol processor works as expected. Also, in our case, process function returns an empty list. This list represents a list of symbols that couldn't be processed in this round and should be deferred to a later round of processing. So KSP supports multiple round processing, but that's a bit advanced topic and it's out of the scope of this talk. So after we've defined our custom annotation, symbol processor provider, and symbol processor, we can verify our KSP setup to make sure if everything works as expected. To do that, we can run this Gradle command. This command will clean build directory and it will assemble debug variant of our application. We also need to specify this info flag to make sure that the logs that we print from our symbol processor are visible in the console output. After we run this command, if we check for KSP logs, we are going to see that the log that we printed from the process method is being visible in the console output. So this means that everything works as expected and symbol processor is being invoked during compilation. We can also look for generated files under the build generated KSP directory, since this directory will contain generated code. For now, we are still not generating anything, so this directory is empty. So resolver is the main component of each symbol processor. So resolver is the entry point to functionalities provided by KSP. In most processors, so the first line of most processors is likely going to be a call to some method on the resolver instance. So for example, you can use get symbols with annotation on the resolver instance to get all the symbols that are annotated with a specific annotation. And there are also other useful components of KSP that are commonly being used. Code generator, which is used for generating files, logger, which we already used, which provides logging capabilities, and processor options, which allow for customization of the processor's behavior. So after we've set up KSP, we can start processing annotations. So we are going to use our generate mapper annotation to annotate all the model classes that need their mappers automatically created. So first thing we have to do is we have to get access to all of the classes that are annotated with this annotation. The logic for that will live inside the process method of our symbol processor. And first, we have to get the fully qualified name of the annotation that we are interested in, which in our case is generate mapper annotation. After that, we can call get symbols with annotation on the resolver instance, pass in the annotation name, and convert the result into a list. So this will give us access to all of the symbols that are annotated with generate mapper annotation. Since we are only interested in class declarations, we can further filter result symbols to only include instances of KS class declaration. So this will give us access to all of the class declarations that are annotated with generate mapper annotation. And to verify if everything works as expected, we can log all of the items of the class declarations list. And if we build our project now, we're going and check for the console output, we're going to see that there's only a single class that's annotated with generate mapper annotation, and that's the person entity data class. So this is what we are expecting to see. Now that we have access to all of the classes that are annotated with generate mapper, we can start generating the actual mappers for these classes. To do that, we are going to use KSP API and Kotlin Poet library. Kotlin Poet is a library developed by Square that simplifies Kotlin code generation and makes the whole process more efficient. So Kotlin Poet provides abstractions for Kotlin syntax, and it allows us to create constructs such as classes, functions, or basically any other Kotlin code construct which makes the whole process of generating Kotlin code more simple and more intuitive. So let's take a look into an example on how we would generate a simple data class with and without Kotlin Poet. To generate this person data class without Kotlin Poet, we have to use string manipulation and string concatenation operations, and we need to handle things such as importing, escaping, and formatting manually by ourselves. So we can see that this code is not very readable, scalable, or maintainable, and if we wanted to add more features here, such as functions, for example, we would end up with even more complex and error-prone code. Kotlin Poet provides us a way to generate Kotlin code using builders, and it handles things such as importing, escaping, and formatting automatically. So the below code snippet will produce exactly the same output as the above code snippet, but with a much more cleaner and simpler syntax. So now that we have access to all the classes that are annotated with generate mapper annotation, we can start creating mappers for these classes. So first we have to extract the name of the name argument from our annotation, because then the value of that name argument is going to be used as the name of our interface component. And to do that, we can use this code block. So let's go through it. First line gives us access to all of the annotations that are applied to a specific class declaration. Then we go through these annotations and we are trying to find an annotation whose fully qualified name equals to generate mapper annotation, since this is the annotation that we are interested in. If such annotation is found, we go through arguments of this annotation and we are trying to find argument named name. And if such argument is found, we get the value of this argument and convert the result into a string. So this will give us the value of the name argument of our generate mapper annotation. For example, if we have person entity data class, which is annotated with generate mapper, and we used db mapper as the value of the name argument, if we build the previous code block and check for the output, we are going to see that db mapper name is being extracted correctly. So now that we have the name of our interface, we can start generating the actual interface and implementation class. To generate an interface with Kotlin Poet, we can use typespec.interfaceBuilder and pass in the name of the interface. And to generate a class, we can use typespec.classBuilder and pass in the name of the class. The name of the class is same as the name of the interface, except that it contains this impl suffix. We also need to add some extra properties to our class. We need to specify that our class implements mapper interface, and we do that by using add interface on the class builder. We are also adding an internal modifier to our class by using add modifiers method on the class builder. So this gives us access to our interface and implementation class builders. Once we have these builders, we can write them into a file. To do that, we need to create a file spec instance, because file spec represents a file in Kotlin Poet. To create a file spec instance, we can use filespec.builder and pass in the name of the file. After that, we use add type on the file spec builder and specify the type that we are writing into this file. In our case, these are the builders that we created in the previous step. Finally, we are calling a build method on the file spec builder to get the file spec instance. And when we have a file spec instance, we can use write2 method on that instance to create an actual file. Write2 method takes in two parameters. First one is code generator and a boolean flag. Code generator represents a path to which this file is going to be written, and boolean flag in our case represents that we want to overwrite any existing file with the same name if it already exists. And if we build our code now, and if we check for the generated code, we're going to see that two files are being generated. dbMapper interface and dbMapper implementation class, which implements dbMapper interface, and it also contains the internal modifier. So two files are being generated, but for now, these interface and class components are empty. So let's add some functions to it. To create a function in Kotlin Poet, we need to create a funspec instance, which represents a function. To create a funspec, we have to use funspec.builder and pass in the name of the function. After that, we are adding an abstract modifier to this function. So this function is going to be used as an interface function, and we need to add this abstract modifier to specify that this function contains no implementation, so it has no body. After that, we need to add a parameter to our function, and parameter consists of parameter name and parameter type. In our case, parameter type is going to be a type of the class from which we are mapping. After that, we need to specify the return type, and we do that by using returns method on the funspec builder. And in our case, return type is going to be a type of the class to which we are mapping. Finally, we are calling a build method on the funspec builder to get a funspec instance. And when we have a funspec instance, we can add it to our interface builder by using add function on the interface builder. Of course, we have to do this before we write our interface builder into a file. And if we build our code now, we are going to see that our generated mapper interface contains map2person method. So we also need to add the same method to our implementation class as well. So code for that will be very similar with two differences. The first one is that instead of using abstract modifier, we are using override modifier, because the class method will implement the method, will override the method from the interface, and also class method will contain the actual logic. So we also will contain the actual code. So to add a code to the funspec instance, we can use add code method on the funspec builder, which takes in a code block instance. So in Kotlin Poet, code block represents a block or a segment of code, and builder function initiates code block creation. After that, we are using add method on the code block builder to add the actual code to this block. And finally, we are calling a build method that creates a code block instance and makes it ready for further processing. To keep the slides short, I'm not showing the actual code that you're adding into this code block because there's nothing KSP specific in it. And if we build our code now, we're going to see that generated dbMapper implementation class overrides map2person method from interface, and it contains the actual mapping logic. And this is how we automate the mapper creation using KSP based on annotations in our code in native Android project. But what about multi-platform? So can we use KSP in multi-platform projects? We can, but a build configuration is a bit different in this case. So instead of having a dependencies block for each compilation target, we have to define a special top-level dependencies block, and here we need to specify which compilation targets will use symbol processing. So to specify that common and JVM targets need symbol processing, we can use this dependencies block. And with this, we've come to an end. So to recap, we are briefly going to look into what are the future plans of KSP, and we are going to go through key takeaways of this presentation. So future plans of KSP focus on three main areas. First one is to support new Kotlin compiler. So everything I talked about in this presentation applies to Kotlin 1 compiler. If you are working with Kotlin, you know that with Kotlin 2.0 version, we also got new K2 compiler. So KSP also needs to be adapted to work with the new Kotlin compiler. Good news is that KSP 2 is already in beta, but there's still more work to be done before a stable release. Other plans include expanding multi-platform support and improving performance. So I already mentioned that KSP is significantly faster than KAPT, but there are still a bunch of optimizations that can be done. And to recap, stop using KAPT and prefer KSP where possible due to performance reasons. So in this talk, we only covered the basics of KSP. We only showed how to generate a simple Kotlin interface and Kotlin class based on annotations in your code. However, KSP is much more powerful than this, and it contains much more advanced features. So I encourage you to dive deeper into KSP and explore how it can benefit your work and help you save time and reduce errors by automating repetitive tasks. And that's it. Thank you all for your attention. And if you have any questions,